ready to do work through review of problems 5 through 8. These are things that will look fairly similar to what you'll see on your exam. So computing OR probabilities for mutually exclusive events. Let's talk a little bit more about that in the context, as I always like to do, of a problem. Okay, there we go. Card is drawn from a regulation deck of 52 cards. What is the probability that the card drawn is a 5 or a 6? So go ahead, try this problem, and then come back and see what I have to say about it. Well, let's think about this. So you can't draw a particular card from a deck and get a 5 and a 6 at the same time. That's mutually exclusive. And so that means that this one is there's less to think about here than there was on the last problem. Here, the probability of drawing a 5 plus the probability of drawing a 6 is the answer. And notice that you could subtract the probability of 5 and 6, but that is necessarily an impossible event, so its probability is 0. So if you want to remember to use the general addition rule for any time you see an OR probability, go for it. Just if the events are mutually exclusive, this part must have probability 0. It has to. It doesn't matter if it wants to or not, it has to. Probability of 5. So let's see here. I believe there are 4 5s in a deck. Plus 4 out of 52 is 8 out of 52, which, of course, 8 is 2 times 2 times 2, and 52, I just happen to know, is 4 times 13, but that's just because I'm weird and I do this all day. And I just want to be sure you have a way to simplify these, because there's not necessarily an easy way to get a fraction in simplest form on a calculator. So that's 2/13. And there it is, 2/13. And again, remember that if you type in a fraction into MyMathLab, it must be in simplest form. And again, this technique of factoring the numerator and denominator and crossing off all the matches between the numerator and denominator, that's the best way I know of to do it. So then if you need to review this, go back to page 270 in your text. Okay, now on to problem 6 that you will likely see on the test. So we're talking about range, sample variance, and standard deviation. And a great resource here is to go enter the homework 5 assignment from module 5 in review mode, then go do problem 14 and click on view an example, and you can see this problem worked out for you. Okay, so now on to example problem 6. We have a pack of M&Ms. You open them and separate the colors. So we've got 12 reds, 18 browns, 25 blues, and 7 yellows. I didn't write this problem. I wonder if someone actually opened a pack of M&Ms and counted them. That would be fun. Now I want M&Ms. Ugh, whatever. Then you put them all back in the package, choose one at random. What is the probability that the M&M is red? What is the probability that the M&M is blue or yellow? Well, try it. Okay, I hope you tried it. And we'll compare your answers to my answers, and we'll see what happens. The probability that an M&M is red should be 12 divided by, let's see, we got to add these up, 30, 55, 62. And that's 2 times 2 times 3, and 62 is 2 times 31. And this is another thing I really like about this factoring technique. I don't know if 31's prime. I think it is, but it doesn't matter because 31 doesn't divide into 2 or 3. So I'm done. 6 on 31. Now the probability that the M&M is blue or yellow, so think about this. How are you going to figure this out? Okay. I'm going to use the general addition rule because if these events are mutually exclusive, it won't matter. I would say they are. I don't see how an M&M can be blue and yellow. It doesn't look like this is a weird pack of M&Ms. So there should be 25 60 seconds plus 7 67ths minus 0 67ths. There are no M&Ms that are blue and yellow. 32 60 seconds. We know that that's 2 times 16, 2 times 31, 16 over 31. So we got, and those are the decimal approximations. 12 out of 62, 0.194. 32 out of 62, 0.516. And notice that this problem didn't specify, are you supposed to give a fraction in simplest form or a decimal? And so I guess we have both now. All right, moving on to question 7 in the world's loudest library, probabilities with independent events. And here's a good example in the textbook to refer back to, but let's do this one anyways. So, among Americans who consider themselves auto racing fans, 59% identify NASCAR stock cars as their favorite type of racing. Suppose that 4 auto racing fans are randomly selected. What is the probability that 2 will identify NASCAR stock cars as their favorite type of racing? What is the probability that all 4 will identify NASCAR stock cars as their favorite type of racing? So, take a moment to think about this problem and see what you come up with. Okay, so we want to know the probability that 2 will identify NASCAR stock cars. So, what are we going to do about this? Well, are you surprised by that outcome? Well, I'm going to actually stop this video because I have to move. I can't concentrate anymore. So I will pick this up where we left off in a moment.